How can you graph them?
We're gonna turn them real then.
Right, they will have real valued solution functions.
Oh, because it'll be e to the I something, so it'll be
Right, it was all cosine and sine. And if it's a complex, if there's a non-zero real part, then you'll have an e to the, e to some power multiplier out front of the sine or cosine. Anyway, we'll hit some of that, yeah. Why don't we do one, let's do one more example, and then we'll take a break. All right, so dx dt equals y. This is a very simple system. And dy dt equals negative x. Okay. All right, unofficially, I want to do a little work on the board for this one. Okay. There we go. All right, so one thing I want to point out is that, in this one it's pretty simple. We got dx dt was what? Was it y or negative y? Y. And dy dt equals negative x. All right, so that's our system. One way of handling this, and it will amount to eliminating the parameter right off the bat. Okay. I can think of dy dx, right? Dy dx, that would be nice to know. Notice there's no parameter t, but we can do that by, this is Leibniz, or chain rule really, dy dt over dx dt, right? That would amount to dy dt, the dt's go away. And what do we get when we do that? Yeah, dy dt, right here, negative x over dx dt, that's just y. Remember this? What kind of equation is this? Think way back to chapter 1. Separable. So it's the parameter is eliminated. And it's separable. Back to those innocent days. All right. So what this looks like is y dy equals negative x dx. So it's not even that hard to separate on this guy. And then what do we do with these? Integrate both sides with respect to the appropriate variable. And we get y squared plus whatever constant you want to call it, but I can just collect them all over to one side really. And this? Over 2?
It's
over 2?
X squared.
X squared over 2 plus C2. Okay. All right. Next step, multiply both sides by, and let's get the constants over to one side, right? I can write this as y squared over 2 plus x squared over 2 equals some constant, call it C3, whatever. C2 minus C1.
It's not really an ellipse, is it?
Is it an ellipse?
Circle.
I mean, it
Those are the
looks like an
same.
ellipse.
Yeah, multiply both sides by the same
Ellipse is
constant,
circle.
2.
A circle is an ellipse. It's
It
like
is.
rectangles and squares, right?
A circle is an ellipse.
It's by definition.
But an ellipse isn't a circle.
Not necessarily.
Rectangles and squares.
Right. Every square is a rectangle, but not every rectangle is a square. So a circle is a special case of an ellipse when there's no distortion. The coefficients in front of each are going to be equal. So we could write this as x squared plus y squared multiplied by 2 equals 2c2 minus whatever, call it c3.
Yeah.
There we go. And we get a circle. Right? With radius root c3.
C4.
Oh, right. So circles. That would be a quick way to know what the trajectory curves are. But notice I don't know the particular solution for x of t and y of t. We eliminated the parameter. This is like x of t squared plus y of t squared for any value of t. Yeah, it's just going to put down a circle. Okay. So Those would be circles. Let's go the eigenvalue route. Get some more practice. All right. So what would be the coefficient matrix? Yeah, kind of weird because 0x plus 1y. So it would be 0, 1, and this would be negative 1x, so my coefficient would be negative 1 plus 0y. So that would be the coefficient matrix. Okay. So let's find the eigenvalues of this. I like those zeros there, make everything a little easier, because when I find the eigenvalues, we're doing determinants a minus lambda I equals 0, and that looks like 0 minus lambda, 0 minus lambda. So I'm going to have, for a determinant, negative lambda times itself, just lambda squared, right? Minus
1.
negative 1.
Plus 1.
Such a simple looking system, and we're going to get imaginary plus or minus I, right? So these are pure imaginary, right? It's of the form 0 plus bi. So that's what that means. The real part is 0. That's pure imaginary. All right. So what's good? What do we do when we got complex eigenvalues? This is the part that was not covered on the exam. Right? I promised there were no complex eigenvector solutions. But we can choose one of them. Okay. The other one, when we pull it apart, it has to do with the fact that the other eigenvalue will be a complex conjugate as well. Okay? So we just need one. So we can take lambda, let's take the positive one, lambda equals I. To find the eigenvalues, then it's just a minus lambda I, a minus lambda capital I, times v equals 0. 0 vector. All right, what does this look like?
Negative I. 1, negative 1, 0, or negative A. Times AB.
Okay. So these should yield the same equations, equivalent equations, but it would be negative I times A plus 1b equals 0. Okay. The other one would be a constant multiple of it. If you write that out, negative 1 times a minus I times b equals 0. And if you multiply the bottom one by I, you get the top one, because minus I squared, that's minus negative 1, is your plus 1. They're the same. So we can just, in other words, b equals I times a, or a times I. So we can just take a to be 1, then b is 1i. So our eigenvector, 1, comma, I. Okay. So remember, this is what I refer to as not the shortcut, but the shorter cut. We're only going to do one of these. We only need to do one complex or imaginary. If I get complex or imaginary eigenvectors, I only need to consider one. We're going to generate the second solution from the imaginary part of this of the solution. All right. All right, so our solution, x of t, any constant multiple, and I'm going to call it c for now, not c1, c2, but it's going to be e times lambda t, and we just got I, times our v. which we got 1i. Okay, so obviously e to the it is going to involve cosine sine, right? Euler's formula, e to the it, will be cosine t plus I sine t. All right. So if I multiply that inside first, I'm going to leave the c out front, but it'd be in the first component, 1 times e to the it, and this would be I e to the it. Okay. Now, using Euler's formula, that constant out front, what am I going to have for, I just said it, but it's going to be cosine t plus I sine t. Okay? The bottom one, I got an I in front of it, but it's going to be the same thing, cosine t plus I sine t. All right, now we want to rearrange this to get the real part and the imaginary part. Oh, I haven't distributed the I yet.
Yeah, or the cosine, or the C rather.
Yeah, I'm going to leave that C hanging out. All right, so C, and the top is just cosine t plus I sine t. Leave some space. The bottom, when I multiply, it's going to be I cosine t. So I'm going to write that over on the right side, plus I cosine t. Okay, is that okay? And what am I going to have over here? When I distribute that I, I'm going to get plus I squared sine t. What's I squared?
-1.
-1. So I'm going to have a -1 sine t. Okay? All right, now, again, leave that constant c out there. What we got is cosine t, negative sine t, plus I times sine t cosine t. Now, this will serve as my two linearly independent solutions. This one, x1, this one, x2. So I just need to extract the real and imaginary part. The reason that works again is because, well, had I considered the other imaginary eigenvalue, negative I, we would have gotten the same thing except with a minus here. It would have given me the complex conjugate of this vector, okay? The complex value vector. Okay, so I could take those as my x1, x2. Finally, my giant solution x would be c1 times x1 bar plus c2 times x2 bar. So c1, and let's just write them in. There's a lot of cosines and sines. Sine, cosine. All right, and then I want to break these out into their component functions. So x of t, notice no bar. I'm pulling out the first component. It would be c1 cosine t plus c2 sine t. Right. And the y of t would be negative c1 sine t plus c2 cosine t. All right, now, can I tell now, are these going to 0? Is either x of t or y of t going to go to 0 as t goes to infinity? No. No, they're just sine cosine curves, same period and constant amplitude, right? Right. Okay, so they're not going to 0. Now here's another, here's a thing we can do. Oh God, then it's going to be seriously time to break. So there's our component functions. That's the solution. But one thing I want to notice is that I'm wondering what's going to happen. I mean, you could write these. Again, we talked about, since they all have the same period, this could be written as a single sine or cosine function. And the amplitude of it would be square root C1 squared plus C2 squared. Same thing could be done over here. Single sine or cosine function, same amplitude. Okay? But what I'm going to show you is that I'm going to square both of them. I'm going to note, since we did that board work up there, x of t squared plus y of t squared. I'm going to square both of these. X squared would be, if you imagine foiling this beast out, c1 squared cosine squared t plus the middle term would be c1 c2 sine t cosine t. I'm going to drop the parentheses for a moment, and I'd have two of them. And my last term in that FOIL would be c2 squared sine squared t plus y squared. I'm going to do the same thing here. Now, when I square the first term in the FOIL, that negative goes away. It's going to be c1 squared sine squared t. The middle term would be a minus c1 c2 sine t cosine t, right? Except there would be two of them. This is the perfect square, right, middle term. And then finally, plus c2 squared cosine squared t. All right, any like terms here? Yeah, look at that. Plus 2c1 c2 sine t cosine t minus 2c1 c2 sine t cosine t. Those guys knock each other out. What we've got left, c1 squared cosine squared t plus c1 squared sine squared. Factor out the c1 squared. And what's going on in here? 1. Cosine squared plus sine squared. Plus, factor out the c2 squares out of each of those terms. And sine squared plus cosine squared gives us 1. So in other words, x squared plus y squared equals
Some new constant c.
c. How about we call it c3? Right? Oh, and this would be a circle with radius root c3. That's square root c1 squared plus c2 squared. That would be the amplitude of each if I wrote it as a single sine curve or a single cosine curve. Square root c1 squared plus c2 squared right there. All right, so what figure do we have here? Figure 5. We got circles. They're not spiraling in towards anything. They have a constant radius. That's figure 7. Now, the question is that an unstable or a stable equilibrium? Look at the point 0, 0. They're centered around circles centered at 0, 0. Is this critical point, 0, 0, is it stable or unstable?
Stable.
Right. It's stable, but they distinguish that in the book, and this is why I didn't want to write this down in words, because it's just, it's paragraphs. Just read the paragraphs. It's stable as opposed to, well, what they say is it's not asymptotically stable, okay? So they don't asymptotically approach 0, 0 like this guy. This would be asymptotically stable because any point here would draw you into it asymptotically. So any point that's near 0, 0 will put you in an orbit that just goes around 0, 0. It'll be a fixed distance, closed curve around that critical point. So it's called stable, but just not asymptotically because it doesn't take that, the point don't get sucked into the critical point.
It's just not going away.
It's like a stable orbit. Think about it like a planet, just orbiting in a closed circuit around it. And so these are all, and that's called a center. So as opposed to a node, we saw nodes up there. This is a center. If we have closed curves around it that always have a finite distance from that critical point.
So if there was an ellipse, it wouldn't be considered stable?
It would.
Like, or it would?
It would. If it's a closed periodic curve
Okay.
around this. So it doesn't have to be a circle. It could be an ellipse, like an orbit of a planet. it has finite distance at any moment, it has a finite distance from that. So it doesn't escape. We call it, yeah, it's stable, but not asymptotically. It doesn't get drawn into that point like this guy here. That would be a stable spiral. This would also be something that involves cosine and sine, but this is what you get. We're not going to do another one of these. This is what you get if you had a complex eigenvalues, because in that point then you have an e to the some power, some amount of power t on the outside of the cosine plus sine, right? And if they're both, and if it's negative, if the real part is negative, so say -2 plus I, then you get e to the -2t, cosine t plus sine t inside, right? So you have some oscillation, but that e to the -2t would force everything to 0. And so this is a stable spiral if I have a negative real part of that complex eigenvalue.
So
It's kind of hard to imagine.
if you have a positive real part, then it'll be an unstable.
Right, so if it was, and here, let me just write down what I'm talking about. If you get lambda that's like -2 plus or minus bi, negative a plus or minus bi, then the solution, after a whole bunch of matrix stuff, right, finding the eigenvectors, you would have something like y of t equals e to the negative at, and a bunch of cosine and sine stuff. In fact, it would be bt plus c2 sine bt, right? This would force it to 0. So if you have a negative real part, this will go to 0. So this would be stable spiral. Okay. On the other hand, if you had, and notice, they always come in conjugate pairs. So if you get a complex eigenvalue pair, they will both have the same real part. So they're going to be both negative a, right? On the other hand, if you have a positive, a plus or minus bi, a greater than 0, then you're going to have a e to the positive at times a bunch of sine and cosine junk. All right? So this would go off to infinity. You have unstable spiral.
For figure 7, why didn't it generate the circles on the far outside?
So what, out here?
Yeah.
Oh,
No, I mean on the left side.
why did it on this side, not on this side? I think it has it on.
Why on the right side and not on the left side?
Why what on the right side? Why are they cut off? It's just because of the window.
There's, he's asking why is there no circles on the
Why are
left
the-
side of
Why are the ones
zero?
that are cut off now kept on the left hand side? Yeah.
Oh, over here.
Yeah.
I don't know. No reason.
It should be.
Yeah.
You're active.
That's good enough. They'll get what I mean here.
So we're going to take a break right now, but we're going to take a look at a couple pictures first. All right. So there's another. This is up online on MyPCC. This is just a way so that you can generate some of these, and I'll just show you real quick. So it's a worksheet, which means it's prepared. When you open it, you got to run that first command with D tool with plots. It loads those graphing libraries and the differential equations library. But each of these is a separate example. Okay, so each of these. So I'm going to go to here. This is the one command, and it does everything in one line. Display P1, P2. And in this case, I think we're going to do something like this. The first differential equation, x prime of t, that's d-i-f-f. There we go. So the first one, x. So x prime equals x. The second equation, derivative of y with respect to t is y of t, so that's just y prime equals y. Okay? If you go down here and hit enter, the semicolon, think for a bit. There we go. So so there's our first guy here. This was the case when A was 1. And we got this proper node. And these were unstable, so this is a source. So it shows the whole phase plane. Okay. And so there's some pre-prepared ones. And in your homework, it asks you to go through and create some of these. You can change these equations. Just look at the general form of the way it's written, right? It shows the independent variable at every step. You can change these and graph your own. All right, this is a different one when k is equal to 2. Yeah, we got the parabolic trajectories. Okay. All right, let's go ahead and take our break. We'll be back in, start in 10 minutes.